Hi, everyone. I get to talk a bit about programming models for SmartNICs. So we'll obviously have to first say, what is a SmartNIC? What does it have on it? What makes it unique? We had a good introduction to Moore's law and the demise thereof in the beginning. And we can have a look at what a SmartNIC does with its transistors, how it can actually fit more capability into the same number of transistors, because the number of transistors ain't going to increase anymore. We'll spend some time on different kinds of data paths. There are pre-programmed data paths that are ready to go. You just plug in a card in your server, load a few drivers, and you can already get the benefits of a SmartNIC that way. There's the option to go and develop firmware yourself in a variety of languages. C you may be familiar with. P4 is a new language, emerging, specific to the domain of networking. There are even hybrids of these that we'll also get into. We'll have a look at a variety of offloading and programming models. For example, transparent acceleration, selective acceleration, where you fall back to the host, different places where you can go and do programming. Very important here is to also consider the different ways in which a NIC can deliver data to the host. Because a network card, after all, has the role of acting as a bridge between the network and the host server. That leads us to the actual performance and cost of ownership benefits of a SmartNICs. And again, these are fundamentally rooted at the silicon level in how much you can do with a transistor, with a picowatt, a joule, etc. And they're then really exposed through the software that's running on that SmartNIC. We'll start to peel the onion further into the actual software architectures and the silicon architectures and look at a bit of example code. I'm not going to go too far into the actual tools and coding, etc., because that's up to you. In the labs later today, you are going to write the software for SmartNICs. And my colleagues will go and introduce you to the tools, the programming environments, but we are going to throw you into the deep end. So you will really see the productivity that you can get with these languages and with these tools. So without further ado, the SmartNIC hardware, you can see it's the standard form factor that you may be familiar with, low profile, half-length PCIe cards, power dissipation less than 25 watts. So these cards are ready to go into your cloud data center, enterprise data center. Very good also for NFV applications. They're based on the silicon, and in that one little chip, we were able to fit, using the optimized architecture, making the most out of every transistor, 72 C programmable cores, 8 threads each. Now that's a huge amount of parallelism, a huge amount of processing capability. And all those cycles per second then translate into a high packet rate. The large number of threads is also very important because while a thread is busy working on another packet, a thread may be able to do memory reads or writes or access accelerators. So these large number of threads and their ability to hide the latency in going to external memory, to PCIe, etc. They're really also important for the performance of the system. A NIC with DRAM, you may not be that familiar with the concept, but if you consider applications like stateful firewalling, where you need to track millions of connections, even if you just consider the classification jobs that these NICs need to do, you need this large DRAM for lookup tables, state tables, etc. So this is really a coprocessor almost, rather than just a traditional NIC. Because of that, it's fully programmable. Whatever you want to do in software, you just write it, explain what to do per packet. It'll do it to many packets in parallel. So this is really SDN as it really should be, not just software being the control plane, but actually software defining the behavior on the data plane on a per packet basis. I didn't show pictures here, but there are also available larger physical NICs that can go up to 100 gig, for example. So you can look at the website netronome.com to see more information about those. So we have this NIC. The firmware is not burnt into silicon. It's not even burnt into flash. You can go and download the firmware from the host. You can actually dynamically, as we'll see a bit later, change the firmware while the NIC is running. That firmware can be pre-programmed. So we already supply drivers and firmware that offer Open vSwitch acceleration, Contrail vRouter acceleration, eBPF XTP on Linux acceleration. In this case, we take advantage of that ability to dynamically change the firmware because we compile the eBPF program into firmware running on the flow processor. All of these can be accelerated by the SmartNIC with the appropriate drivers and firmware being supplied. You can also go and develop the firmware yourself in languages like P4 and C. That's what the later labs will be about. You'll actually go and do that. There's the normal development environment. You can write P4 code, C code. There's hybrids possible where you can have C embedded in P4. Other hybrids can also be conceived like C as a little sandbox next to OVS, eBPF combined with OVS, etc., etc. So this is quite a friendly development environment for the normal edit, compile, debug, optimize cycle that you're all familiar with. The development environment can connect to hardware over the network. So you have a little agent running in your server, allowing you to debug things in place in a real network, while the front end, the GUI, is maybe running on your laptop. What we'll see later today is we actually set up a bunch of real servers for you to work with. And because some may not want to load the IDE on your own laptops, we're giving you VMs running the IDE already configured. And you'll just use remote desktop to get to those VMs and actually do this programming. So this also features a runtime environment by which you can download code, but also interact with the match action tables, the same way as you would normally use OpenFlow. So let's look in a bit more detail at these various options of pre-programmed and custom firmware and how they can be permuted and combined. The basic case is, let's say there's a server with some kind of CPU. These days, it's typically Intel x86 that predominates, but it could be other CPU types. There may be a data path already on that server. It could be in the kernel, it could be in user mode, it could be the kernel being the fast path and the user mode being the slow path, as you can find in, for example, the OVS kernel version, etc. And I didn't show it here because the picture was getting a bit complex, but there's also a control plane with something like OpenStack, OpenDaylight, etc., going and provisioning the whole network with policies that need to be applied. So the transparent drop-in replacement concept says that we're effectively going to not use that data path much in the server. We're going to have the equivalent functionality of that data path offloaded onto the SmartNIC. And whether it's matching, actions, tunneling, QoS, metering, all the features of the host data path, we can go and implement on the SmartNIC, because you remember it's got fully programmable cores. It's in fact got more cores and threads than even the biggest server. And it's got gigabytes of DRAM. So whatever you throw at the server, the NIC can just do. And that's why the data path here becomes a dotted line. It becomes almost more like the control path to just get the match action tables into the NIC. So the idea here is that the majority of the traffic will actually just go port to port on the NIC. Of course, it can go to VMs as well if you're hosting VMs. There's the concept of fallback processing, though. Now, what do we mean by that? There may be certain categories of traffic that you do not want to offload, that you do not need to offload. The example I like to cite is ARP, address resolution traffic. If you're having 10, 20, 30 million packets per second of ARP traffic in your network, and you really need to speed that up using a SmartNIC, you're doing something badly wrong. And I'm sorry, we're not going to aid and abet you in that madness. So we are not going to give you a data path that delivers 20 million packets per second of ARP to the host. That is a clear case of traffic that can take the fallback path. Another case that always has to fall back is the actual control traffic. Let's say OpenFlow that needs to go to the host, which is implementing the control path. So it could be the provisioning of tables over the network. It could be packet in, packet out, needing to go to the controller, or statistics going back to the controller, etc. So these packets will follow the red path and still go to the CPU. Another case to be considered is new features that are maybe added to the CPU data path that haven't been implemented in the offloaded data path yet. So these new actions or match fields, if they encountered, it would just transparently fall back to the host, not be accelerated, but at least work. So this is a very important concept to look for in SmartNIC data paths. Does it have a fallback option, or is it whatever you do on the NIC is all you get and there's nothing else? So as I mentioned, this being a NIC, it won't just forward traffic port to port. It will also act as a NIC for VMs and apps running on the host. So this being the history museum, of computers, we also have to consider the time dimension and how these things roll out over time. What we've already implemented as offloaded data paths include OVS, in other words, OpenFlow, match action, tunneling, many different tunnel protocols, VXLAN, GRE, combinations with MPLS, etc., etc. Control vRouter has also been offloaded in the same way. Again, matching actions, tunneling. There's the Linux contract facility doing firewalling. That's available. vRouter has its own firewalling capability embedded. All these are offloaded, and eBPF XDP is also transparently offloaded in this way. The next level of flexibility is where you actually do want to start programming, but you may not want to program the SmartNIC. You have an app calling an API on the CPU, and this is to use an analogy from the graphics world, similar to, for example, OpenGL. You may actually write your game and you call OpenGL to do rendering of 3D things, and you kind of just ask it to do the rendering for you. You don't know whether it's an NVIDIA or an AMD ATI card underneath, or just software with a frame buffer. You don't program the shaders yourself. You just tell OpenGL what to do, and it goes and does it. And this model is very similar. So you would interact with an API on the host, telling the data path there what to do, and that data path is offloaded to the SmartNIC, but the same behavior occurs. So examples of APIs that follow in this category are DPDK Palmo driver, can get packets. There's emerging efforts to add various APIs to allow offload. For example, eBPF XDP, we can support the existing APIs and just offload it. So if you have an API working with a map in eBPF to access the content of the map, or get the information back using the perf kernel to user mode interface, that would just work. Some of you in the audience here have been at the various other events earlier this week. It's been quite a busy week with 5 different conferences happening in the area here. And there we started to discuss offload APIs, like matching, action, tunnel, etc. APIs. And these could be in the kernel, in user mode, various areas. Again, if we are compatible with those, it just works on the SmartNIC without having to program the SmartNIC itself. The further evolution is to go to a fully flexible data path, where one is not constrained by the choices that were made in the OpenFlow standard, which OVS then implemented, or the choices by vRouter of how to arrange the tables. vRouter, for example, decided to do a flow table with policies, firewalling, and so on, and a forwarding table governing the forwarding. And that's their choice. That's just how it works. With this flexible model, you can change it at any time. You can add a table, you can do matching and actions and more matching. In OpenFlow, we had to change the standard when we said, okay, we want ingress tables, group table, and egress tables. Here, you can do whatever you want. You can even do QoS in the middle of the data path, not just at egress, for example. The data path here would be expressed in languages like P4. You could also express it in C, of course. And because even the parsing, even the fields that are used in matching are fully flexible, you can introduce new data plane protocols. Let's say you want to have your own tunnel protocol, or you want to add telemetry headers. All these things are possible with a fully flexible data path. Again, it can be combined with the existing things. So if you could have the full flexibility on the host, which is then offloaded, or you could program it only on the SmartNIC and kind of just treat the host as more like a I/O destination, an origin of packets. As far as hybrid deployments, we have the ability using something we call the plug-in concept or the sandbox concept, the ability to embed a little bit of code inside an existing data path. So you'll see it in the labs later today that you can, for example, have a P4 data path, and that can then embed little C function to do additional processing on packets. What could one do with that? One could, for example, do a custom tunnel that way. The outer layers would still be handled using the existing data path match action. So your match action may say, okay, it's IP traffic, it's UDP traffic, it's the UDP port belonging to the custom tunnel. Let me hand off that to the C code, which then goes and parses within the UDP what goes on. So you have these two layers of classification going on. The outer, done in the existing data path, done in whatever existing way, OVS, P4, vRouter, and the inner would be done by the plugin or the sandbox. Similarly, it's very easy to do custom actions, where your outer would decide when is the action having to be done, and the inner would just go and implement the action. What's a little bit harder, and that's why I put it lower down in the time sequence, is custom matching, where you, for example, want to say, okay, we have a match table, and whether a row matches or not is a combination of existing match action ACL table style and a C expression that says, should this row match? That's just semantically a bit harder because we need to extend the likes of OpenFlow and the vRouter protocols to go and make the matching extensible for the outer protocols at that level, but it's still possible. So let's delve a little bit into the NIC features and the intricacies of actually delivering the data to the virtual machines or the host in general. The simplest one to consider is the SR-IOV model, where SR-IOV really has got other synonyms like PCIe device assignment. It effectively means that the VM can map a certain queue directly into the NIC. And it looks like a device on the PCIe bus and so-called virtual function rather than physical function, but still it's a device on the PCIe bus. And you interact with that device, configure it a little bit, get packets back and forth. There's some configuration supportable here, and there is some support in, for example, OpenStack to configure SR-IOV NICs. The configuration comes via user space agents and plugins, and it then configures the hardware. Once the hardware is configured, the user space kind of fades away and is not doing anything anymore. And now the traffic can go from the ports on the NIC via this traffic director. I used a generic term here. I don't know what the different vendors use, to the VMs. So it's normally very simple operations that can be done there. You can maybe map a physical port over into a virtual function, Sometimes you can do an exact match on things like a MAC address or a VLAN tag. But it's really only few simple fields directing the traffic to the right virtual function. So the expressiveness of this solution is quite low. It's certainly not something you can call switching, let alone something you can use for security or tunneling or any of these things. Because you have this direct path and you're not doing a lot per packet, it's actually possible for many vendors to give you high performance this way, because all they have to do is shuffle packets back and forth. But because of the SR-IOV really letting your VM have a direct session, so to speak, with the hardware, you have really poor manageability. Your VMs get kind of tied into your hardware. And if you want to go and migrate that VM to another place, it's similar to doing a hot plug of a card out and plug another card in. It could be a different vendor's card on the place where you're migrating to. Even if it's exactly the same thing, your virtual function number could change. So it ends up being that the benefit of all the cloud technologies of being able to be flexible is lost, because you're now effectively building an embedded system. Things are tied to the hardware. You may as well not use VMs. You're almost like running directly on the hardware. The alternative is to now have the host running the data path. Here you actually get a lot more complicated configuration from the cloud management system. You would have the option in OpenStack, for example, of going directly to your control agent. There's another option to go via Open Daylight. Open Daylight can then speak OpenFlow to the control agent. Our friends at VMware developed OVN, which is a different protocol running in the cloud, and then OpenFlow is only used locally. So there's many different options. So you can even use a command line to just quickly set it up. Matching the actions that all be done in software. I show the kernel version here, could as well be some matching and actions done in user space for the fallback path, etc., etc. And then the link to the VM would be in the server, memory-based. That's where things like vert.io, various other VETH pairs, tap devices, etc. come in there. The user space agent would typically populate the kernel table somehow, maybe as triggered by a packet, maybe preemptively, depends on the system. And then traffic would run via the host software to the virtual machines. The control agent, again, doesn't need to be in the picture once things have warmed up and all the tables have been populated. So this gives us much higher expressiveness in the software, but it consumes cores. Alternatively, if you want to constrain the cores to a reasonable value, then you get quite low performance. So, so this is certainly very flexible, but for high-performance networking, this is not acceptable. And also for the environment, this isn't very good, because you have expensive, power-hungry cores doing the work here. Now, to give you an example of an offload model with a SmartNIC, I used the example of the Agilio SmartNIC, but it could be any SmartNIC really that's fully programmable that could do some of these things. So here, you would again have your configuration. You would send that to your agent. And in the SmartNICs case, remember we've got gigabytes of memory, many cores, and so on, so we can fully implement that data path that was there on the host. In the OVS case, tables start out as empty, and packets then get sent to the kernel using the fallback mechanism, go to user space, go to the OpenFlow, match action tables there. They will populate things into the kernel data path, which is more like a masked exact match, the so-called megaflows, and those will then get offloaded onto the SmartNIC. And in addition to that, on these SmartNICs, we also have an exact match flow tracker up front to further speed up matching. The net of it is that even contract firewalling could be offloaded in the same way, with the tables being synchronized. So the net of this is that you can have full functionality, but you can still have the SR-IOV style direct connection to your VMs, or your vert.io capabilities are still available as well, if you prefer vert.io. We'll see a bit later the P4 and the C options, where these would be brought in as the little plugins or the little sandboxes working in conjunction with this. So this gives you the best of all the worlds here. You can get the performance of SR-IOV, you can get the flexibility of vert.io supporting things like VM migration, and still the core saving related to switching on the SmartNIC.
Go back to slides.
Yeah. 2. Yeah.
Previous one.
Oh, the previous full slide, okay. Yeah. One more, okay.
Yeah, this one. Poor manageability.
Yes.
Right? How are you solving that problem with the outflow?
The poor manageability refers to the fact that you don't have VM migration here, so you cannot go and move things around. And let's say you want to do a software upgrade on your server and migrate a VM, do an upgrade, migrate it back. Or maybe you want to do a hardware upgrade. These things will just die because they're tied to the to the server. Whereas if you have the ability to do vert.io, you can go and migrate VMs around, and that allows you to have the resilience for things like upgrades. Let's talk about network policies. Here you do not have any expressiveness in your policies. You're tying your VM to a MAC or a VLAN address. Whereas if you have a proper policy, you can do things like tunneling. You can do things like network address translation. You can put rules in there with statistics to give you information on what is happening in the network. Or let's say you're debugging issues. You can put a rule in to go and mirror traffic. So there's a lot of flexibility in how you do your overlays and how you debug your networks that you don't have here. Whereas if you actually had below your virtual machines, all that flexibility, that already gives you better manageability. But also the vert.io link allows you to do the migration and the software upgrades, hardware upgrades, etc.
What about the state migration, which is that if you have a stateful firewall or some stateful NFP, whether it's running in OVS or whether it's running the SmartNIC, all that state also has to migrate. So it seems that you still have a problem with the state migration.
You do, and that is, of course, the VM itself that's migrated is a lot of state, right? But that is a problem that's being addressed anyway. By migrating the VMs, they migrate the pages gradually if you do live migration. And then at some point, you quiesce the VM, copy all the remaining dirty pages over and so on. We all know that. But very similarly, the firewall rules would also be migrated. In the case where you move the MAC address or the IP address, you take care of the network traffic. If you do not move them over, there's the notion of hairpinning traffic, where traffic may still go to the old place a little bit. And if you have a SmartNIC there, you can have a SmartNIC actually receive that traffic and go and forward it on to the new place where things are running. Until everybody learns of a new location, let's say the bridge, MAC learning, new ARP entry takes effect, etc. So that is basically a solved problem already in the host side. And because the SmartNIC only offloads it, you basically, as long as it's synchronized properly with those host mechanisms, the SmartNIC still supports the migration of that state.
So your argument is that the VNF state migration has to be handled by the application, and you claim that the application already solves that problem. I'm not sure, I'm convinced, but it creates a problem that you need to solve.
Yeah, the VNF itself, that of course is VNF specific, and we can give some infrastructure to help, but I was more referring to the state that is underlying the VNFs. For example, the state in this contract module. Yeah, that's like the stateful firewalling state and so on. Okay, so let's have a look a little bit at the actual performance benefits we get here. So this is measurements on OVS in kernel space, OVS in user space, and the offloaded OVS as an example. You can see higher throughput, depending on what you compare it to, different factors of throughput, but look at the number of cores that were consumed here. The offloaded one only used a fraction of a core because all the work is done on the SmartNIC, whereas the baseline used 12 cores. In other words, one of the two sockets in a two-socket system to go and do the work. So to visualize it, you really freeing up almost a whole socket in a two-socket system for application and VM processing. And that is really the value proposition here. Because it may not all be networking bound, it depends on the case exactly how much you can save at the data center level, but I'll encourage you to go to this ROI calculator that allows you to type in your own values of cost of a NIC, throughput needed per VNF, per app, etc., and it will tell you what you could potentially save with the SmartNICs. So all these benefits can also be achieved with a fully custom data path in something like P4. So you could do all these things, vert.io, SR-IOV, matching and actions with control in P4. There is a little yellow note here. We need to go and, as an industry, develop the successor of the OpenFlow protocol, because OpenFlow is not good enough for all the flexibility that's in P4. OpenFlow doesn't allow you to dynamically define a parser, dynamically define new data path protocols, etc., etc. But conceptually, it's the same. So to summarize, you have higher expressiveness, high throughput, and the manageability benefits if you have a SmartNIC compared to your baseline. Since I already covered a lot of this answering a question, I'll just move on. So delving into now the actual flow processor silicon. We're having many cores. The cores do things like your receive and transmit on PCIe, on the network, including tunneling, match action processing, etc., etc. So all of that is just expressed in software. Then the chip actually has IOs. PCI is an I/O, Ethernet's an I/O, and it can have the DDR for the millions of rules. These function accelerators you see there, they effectively almost like subroutines implemented in hardware. And that's also how they're exposed at the level of the programming. So you could have a job you need to do, keep a statistic that you would send to the atomic engine to atomically increment a counter. You could have a job you need to do some hashing for a table lookup, and that can use these function accelerators. And this way, you don't really notice that they are function accelerators. They just look like subroutines or additional instructions. You'll get to do this a bit later in the day. Here is how, yeah. What atomic refers to is if you have a normal processor, you need to read things, for example, to increment a counter and then increment in a register and then write again. And that's a kind of a pain if you have many threads trying to do it simultaneously. So what we implemented is, we call it an atomic engine, which will atomically read, modify, write, to do certain things. And that way you don't need to, in software, go and say lock, read, do stuff, write, unlock. And that atomic engine, thank you for the question, by the way. It's great to be able to talk about this. That allows all the different engines to just work with the same counters, with the same data structures, without getting in each other's way and without needing to lock and unlock. Yeah. Yeah. Sorry? Yeah, the question was, what are the limitations for the style of programming? I think the next slides will actually cover this. So let's maybe just look at the next ones and you'll repeat the question if it doesn't answer it. Okay. Yeah, I'm going to go a little bit over the time in the agenda here because we had such great questions. I think it makes sense to answer them in detail. So here's really the style of programming that this enables. There's hardware up front that can load balance to processing cores. And these processing cores now, for example, run P4 code that will do parsing, matching, actions. You may actually get a thread that can finish its work on a packet quickly and another thread taking long, and that may cause packet reordering. So there's an actual hardware reordering engine in these systems to maintain the original packet order. And the style of programming then is, to your question, run to completion. You just say what you want done to one packet. And the system will take care of repeating that for all the traffic that comes in. If you want, with these fully programmable SmartNICs, you can mix P4 and C code. So I've got the C plugin there, which is like the sandbox concept. The picture could be exactly the same if you write it in C instead of P4. You can write your own parsing, matching actions, call into C subroutines in C as well. If you prefer, you can make your own topology of processing stages. So you can make effectively your own pipeline. You can have stage one feed with what we call a work queue or a ring, packets to another one, and you can keep going. So really the style of programming is up to you. If you prefer everything in one, fine. If you want to build up a pipeline, another topology, that's also fine. And here is an example of P4, because some people may not be familiar. You'll get a lot of time in the labs to dig into this. An example of P4 doing a simple NIC, where you declare header fields, you declare passing. If you wanted to go on here with IP, you would have declared IP and say ether type 0800 means have to pass IP. You declare the need to do matching on a port in this case, and then you put in table entries that say physical port 0 goes to this virtual function port goes to that other physical port. We could have matched more than just the ingress port. We could have matched on IP or Ethernet, and we do the actions. So this shows in P4, we just say what the system should do, match an action, not how it should do it. And we then compile that to the highly optimized firmware directly. Here's an example of C code. You call a function to receive a packet. You call another function to transmit a packet. Again, expressing what to do packet by packet, and it will automatically run this effectively main function on all the different cores in parallel. So here's an example of a fully customized data path where you write the blue parts are written, for example, in P4, and the red parts were done in C. This is a demo we did. And conceptually, the control app has a runtime interface going via the agent to get access to the tables and statistics, but your development environment also gives you a way to get access to the tables, to interact with it, which you'll see in all the remaining labs. Does this cover your question? There's basically no limitations to the programming flexibility by these architectures. Okay, yeah.
You might have been talking about like resource limits, like how much memory you can use before caching. I know maybe there's hardware limits.
Yes, of course, there are always limits like that, and there is significant memory on chip, but also because this category of SmartNIC has gigabytes of DRAM off chip, and you can actually use that DRAM for lookup tables, for packet buffers, for queues, even for statistics. So if you want to do metering and you want to go and implement 1 million meters, by meter here I mean like rate limiters, you're free to do that. So there aren't that many constraints here because of the availability of DRAM. Only data. Code in these ones is on chip only for performance reasons. Yeah.
Quickly highlight what are the trade-offs of using P4 versus C, and in the example you are showing, what are the reasons why some modules are written in C and others? Is it because of limitation of one versus the other?
Yes. So P4 is good at declaring new protocols and saying how do you want to match them, and the actions you can do in P4 are kind of field-oriented. So the action may be push a header or set a header value to another thing. So that first block there, match protocol, is it TCP, then go and do metering. That's fine in P4 because it has the concept of a meter, which you're going to play with a bit later. That security MicroVNF there, let's say that's an intrusion detection system and it wants to look for a pattern in the payload. P4 doesn't have the notion of a string and searching in a string and iterating over the bytes in the payload, because the actions are not very sophisticated. It doesn't have pointers, it doesn't have indexed access to the payload. The timestamping, putting in a timestamp as a packet header, fine in P4. The statistics for latency and keeping, for example, a state table, P4 can do math, but it cannot really do a state table and put data in an array. with a complicated index yet. The language is being extended. We're recommending adding that, for example, but we're not there yet. So that kind of gives you an idea of the kinds of things. Yep.
What do you mean by the MicroVNFs that are running on the SmartNIC? Are we going to have to deal with this when we do the data programming, or those are automatically established for any function that we look at before?
Yeah,
How come are we going to really expose to us at this point?
Yeah, so that's a great question. So I think MicroVNF is just kind of a term that emerged in the industry to say that you may have a full-blown VNF running on your host in virtual machines. And you could have a MicroVNF running in the fast path as well. With these flexible processors, that becomes possible. Now, remember the beginning slides. If you are doing transparent offload, then by definition, you're only exposing the host side. And in the SmartNIC side, transparently helps. So in that case, let's say let's take the security one that's on the slide here. If that security MicroVNF searches for $ in packets because a certain intrusion has a $ as one of its characteristics. And then it can pre-filter the traffic and feed it to the VNF in VM1, which says, okay, anything with a $ I need to examine more. And I need to check, is it this signature of the worm in the traffic? And now, okay, I know. So it can already do some pre-filtering. In this case, the MicroVNF and the host side work together. The one offloads the other. And then at the network layer, you don't really see it. You don't have to deal with it. It's just transparent acceleration. In the case where the MicroVNF is separate from the host, and it is really almost like part of your infrastructure, part of NFVI below the VNFs, then it's a separate item that you would separately manage, compile the code, download the code, etc., etc.
So we have control over creating those, or the automatically created based on the infrastructure?
The programmer would really instantiate them in the program. So whoever does the programming, if the programming is done by the infrastructure guy, then that would be done. If the program is more like done, let's say it's more like a single function compute node, then the programming may be more like tied to the VNF programming. So it kind of depends on who is doing the programming, when they would be instantiated. But
Do I have control over how many threads can be assigned to those MicroVNFs?
yes. Yep. Yep. Okay. A lot of great questions.
Simple question. Do you intend to make these slides available online, or do I need to take pictures of all of them?
I think we're going to post them, and there's also videos.
Yeah, they'll all be there on the website.
Open-NFP.org. That's where they'll be posted.
You mentioned one example where P4 originally was designed for switch use cases, had some more things to be done to handle the NIC use cases.
Yes.
Can you elaborate a bit more on what was needed, what you have suggested to be enhanced, and what is not yet there?
Certainly. So there's a few categories of things in P4. The question for those that didn't hear, how does P4 need to be enhanced for NIC versus switch? The most basic one is exposing the fact that it's a NIC and that it doesn't only have physical ports. Well, that's actually very easy because we simply introduce another set of numbers that may be numbers 0, 1 to 3 are physical ports, and 1 to 8, 1 to 9, and so on are the virtual ports going into the VMs. But if you look at, for example, what it actually does, being a NIC, there are features like checksum offloading. There are features like a link state that need to be made available to the host to be a proper NIC. So there need to be extensions to really interface with the features that are needed by a NetDev, which you wouldn't actually get on a physical port, because on a physical port you have Ethernet, and there's no metadata on the Ethernet going with the packet. Whereas with a NIC, you give a packet to the host with some metadata. Were checksums offloaded? Were they valid, and so forth. The other category of things are less related to the plumbing, but more features. So, for example, the things that are typically done on a NIC may be more stateful features.
Sorry, on the previous point, right?
Yeah.
Before LOs, right, where you can add a header with the metadata, right, so we can pass it up actually. So do not need solving your point actually. We need to give more metadata for the traffic going to the NIC, so that should solve, right?
You could do that, yes, but for interoperability reasons, you may want to define some kind of an agreed-on way of doing it, such that every P4 programmer doesn't also have to be a kernel programmer and have to write a native code that interprets that custom metadata. So it's more a matter of standardization, yeah. Now, the other things that are needed are more like things that are typically done in these servers, like stateful firewalling, or allowing the VNF and the MicroVNF to talk to each other in an efficient way, in high performance. Use the example of an IPS that I mentioned, where that IPS in C code in the VM may want to share tables with the IPS running in the SmartNIC. And this concept of the plugins, the C plugin in P4, that is also not necessarily done in the same way in a switch. It may not be a plugin in the fast path in a switch. It might more be like a control processor plugin. Okay, we do need to wrap up, I guess. So to summarize, we looked at the two main ways of using these SmartNICs. There are the existing data planes that you can just use as is. Plug in the card, load drivers, get a lot of TCO benefits or just higher performance. You can go and program the SmartNICs. I have a lot of sessions on that upcoming. And a third request here I have is really this is a community-driven effort to go and extend P4 for SmartNICs, as we just heard, to go and define that runtime interface that allows you to get at the match action tables in the SmartNIC from your cloud management system, from your VNF, trying to access tables, and so on. So it would be really great if people could participate more in these various bodies. Another example I can use from this week is discussions starting up or continuing on acceleration APIs for Linux, DPDK, and the like. So please do participate and enjoy the benefits of a SmartNIC. More flexibility, higher performance, and freeing up the server resources. And really, Moore's law is gone, but this way you can get more benefits out of every transistor and still support the 4G, 5G, 6G style network throughput improvements we all depend on with our smartphones and other devices.